people in the world uses the decimal number system, which has 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's it. Use these 10 digits, and after that, we write the number of tens and then the number of ones until we reach 10 squared. Then we write the number of 10 squares, which is hundreds and tens of ones. Yeah, that's basically how base this works, specifically base 10. But if we didn't make 10 base, if we didn't write the number of tens on tens place, if we had a 12th place where we write the number of 12s on, that's basically the Dozenal system, which has 12 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and back, L, and then after that we have O, which represents the 1 means 1/12, and the 0 means nothing more. Of course, they say 1/12. They use 1 dough, and then and there's 1 meaning 1 dough and 1 dough and 2, and so on. So this is a small system. Keep in mind that these 2 digits are set in stone. They can be anything. I'm just using the Pitman digits. You can also use Argam. You could use Dwiggins. You could even use alphanumeric. I'm just using Pitman because I like. Anyways, now there are lots of decimal folks in the world, and they argue that decimal is better than decimal. Well, yeah. First, we use decimal for a reason, because we have 10 fingers. Come on, like when our civilization, when the human civilization evolved, they first start out counting on fingers. And heck, even the babies now, even our toddlers start out by counting on fingers. We all count on fingers, and since we have 10 fingers, it's really easy to do that. Yeah. Well, I'm pretty sure Stanford Pines would approve of decimal because he has 12 fingers. So yeah. It's decimal is just a tradition that we preserve, and we can't just switch to decimal. But what makes decimal so good? Well, it's mostly because 12 has a lot of factors. 12 is highly composite. It has like 6 factors: 1, 2, 3, 4, 5. Wait, there's no 5. Why not write a 5? 1, 2, 3, 4, 6, and 12 is self. Yeah. And 10, well, 10 is the semi-prime. It only has 4 factors: 1, 2, 5, and the self. So, by this logic, since these are all factors of 12, multiples of these will be very easy to identify in decimal. Like numbers that end in 0, 2, 2 times 2 is 4, 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is stack. I use Pinman, so yeah, this is also argument death, but whatever. Anything that ends in these will be multiples of 2. So we have an extremely easy divisibility for test for 2. We can also say this even decimal. We have, if it ends in 2, 0, 2, 4, 6, or 8, it's gonna be a multiple of 2. So we both have to add the divisibility test, but decimal also has an extremely easy identification of multiples of 3. If it ends in a 0 says multiples of dough and 0, and dough is multiple of 3. This is base 12. 0. You know what? I'm actually gonna write it down here because we're being way too decimal centuries. Now, 3 multiples and then 0, 3, 6, or 9. So it's also easy to identify. 4 multiples and then 0, 4, or 8. 6 multiples and then 0 or 6. Well, decimal, there's only one other easy identification method, which is just 5. Multiples of 5 and then 0 or 5. That's one of the reasons people consider decimal to be better than decimal, because of these divisibility tests. But when you think about it, decimal actually has more divisibility tests than decimal. More easy ones at least. Alright, we know that in decimal we have the divisibility test for 2 and 5, right? But actually we do have one for 4. We know that 4 times 25 is 100, right? 100 is a multiple of 4, which means like if we have a number 3, 5, 7, 2, 1, 8, 4, 5, 6. Like, and I'm gonna ask you, is it a multiple of 4 or not? Well, since we can just split it up into 3, 5, 7, 2, 1, 8, 4, 0, 0, and 56. Since 100 is a multiple of 4, this is already a multiple of 4. We know that. That leaves us with 56. 56 is also a multiple of 4. So yeah, this big thing is a multiple of 4. So it's actually an easy way to see if a number is a multiple of 4 or not. Let's look at the last 2 digits. Well, it does require you to memorize the 4 times table up to 100, but most people in the Learning Blocks community actually memorize that. Because they have to memorize the factorization of numbers up to 100 to make the sign for them. So yeah, we do have a divisibility test for 4. Gonna add that in. Now, what about 3? Do you have the divisibility test for 3? Like, is this thing 5, 6, 2, 7, 8, 4, 3, 3, 9, 1, 0, 2, like 2, 1, 4. Now we want to know if this thing is a multiple of 3 or not. How do we do this? Well, we add up all the digits. That's literally how we do it. We add all digits, 5, 7, plus signs and all of these. That is equal to, in fact, let's just check the number bonds. Let's see, 6 as multiple, that's already a multiple of 3. But you know what, let's just do this. This is 13, 11, 13, 20, 28, 32, 35, 38, 47, 48, 50, 54. This is equal to 54, and 54 is a multiple of 3, so this abomination without the plus signs is a multiple of 3. How do we know that? Well, there's actually proof to this. So, you know how 9 is a multiple of 3, right? 99 is also a multiple of 3, and 999 It's also a multiple of 3. In fact, let's just write a whole bunch of 9s and i's. And that's going to be a multiple of 3. It's also going to be a multiple of 9. So for all of these, we have place value, decimal place value. We have 10, which is 9 plus 1. We have 100, which is 99 plus 1. We have 1,000, which is 999 plus 1. We have 10,000, which is 999,999 plus 1. And so, place value, we have A on the ones place, and then we have B on the tens place. It's going to be 9B plus B. If we had C on the hundreds place, we also had a number like this. CBA are all digits. We have 99C plus C, and then without 4 digits, DCBA, we will have 999 D plus another D. We have 5 digits. We have 9,999 D plus E. It's supposed to be E plus another E, and we can basically go on forever. Now we know 9 is multiple of 3. This is a 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 multiple of 3. These are all multiples of 3. E. So we can just ignore them. If the rest of these are multiples of 3, then this whole thing is a multiple of 3. So if A plus B plus C plus D plus E plus whatever goes on is a multiple of 3, then A, B, C, D, E, blah, 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 this number goes on. It's going to be a multiple of 3. And of course, the same thing works as for 9 as well, since all of these are also multiples of 9. 9, 9, 9, 9, or 9, 9, 9, 9, 9, 9, bunch of 9s. Well, if this thing is a multiple of 9, then this thing is also going to be a multiple of 9. Yeah, it works. Generally, this also works for different bases. This works for the divisibility test for base minus 1 and all of its factors. Well, since we're using base 10 now, this works for 10 plus minus 1 is 9. This works for 9. And since 3 is a factor of 9, it also works for 3. So we do have the divisibility test for 3. But unfortunately, in Dozenal, well, that's Do minus 1 equals L. And L is a prime number, which means it's only gonna yield one divisibility test, unlike in decimal where we can yield 2. Ooh. We got 3 and 9 out of that divisibility test. We got 2 out of 1, while in decimal we only get out, and that's it. Anyways, let's continue on. Since we have 2 and we have 3, and then we can have 6, right? It's not hard. If we have 2, we have 4, we actually do have an 8, but it's not that easy. We have to look at the last 3 digits. So example 3, 4, 2, 9, 8, 1, 6. Is this thing a multiple of 8? We look at the last 3 digits. Oh, it's this. Here's an 8. Here's a 16. It's a multiple of 8. Well, this is an easy one since this is obvious multiple of 8. This whole thing is multiple of 8, but usually you're not gonna get a not so obvious one, and you have to actually divide this 3 digit by 8 to see if it's multiple of 8 or not. It's a normal division. So this is a debatable test, but it's definitely useful for chopping down some real long numbers. Like, what if we had a bunch more digits over here? Yeah, this is still kind of useful. So I'm gonna count this in with a different color. Yeah. Well, by a similar logic, you could get a similar logic of decimal 4. You could get 8. Here's the divisibility test for 8 in decimal. Since this is 100, this is not 100, this is grow. This is decimal. So this, you have to, this is a multiple of 8. And so we can, by same logic as decimal 4, we get an easy divisibility test for 8. But then we realize something. Okay. And it's also a multiple of 9, so we can, and by same logic, get the divisibility test for 9. But then we realize something. We can't get the divisibility test for 5. We can't get one for 5. We can't get one for 7 either. So we can't have one for 5. We can't have one for that. In decimal, we can't have one for 7, but we can have one for other digits. Well, 8 is debatable, but then again, it can be cut down. There's no easy divisibility test for 5, 7, and that. So, Dozenalists, if you're going to argue over the divisibility test, then now. And by the way, these all have, there's always an easy divisibility test for base plus 1. It all exists. You add up the odd digits. Suppose we have some 3, 8, 5, 7, 4, 0, 0, 2. What do? You skip count. You skip count from here. You add up these 4 and mark them pink, and then you also add up these 4. Yeah, mark them green, and then you subtract the green from the pinks. You take the difference and see if it's a multiple of base plus 1, the number we asked is, or not. Yeah, it's pretty easy. Anywho, these are the divisibility tests in decimal and decimal. And now this video is done. Bye!